Welcome to today's Explainer. Today, we're taking a completely fresh look at the thermodynamics of condensation and boiling. We're going to take some of those incredibly dense engineering equations and transform them into a visual journey through phase changes, really uncovering the precise mechanisms that drive modern thermal engineering.
Here is our roadmap for today. 1. The power of phase changes. 2. Film versus Dropwise condensation. 3. Math of the condensation film. 4. The 6 regimes of boiling. And 5. The drama of bubble growth.
Section 1. The power of phase changes.
So why do phase changes even matter? Well, if you're looking at a standard single-phase system, heat transfer is honestly pretty straightforward. But when we're talking about the massive heat transfer rates needed to actually run commercial power plants, or even just your everyday home AC unit, we rely entirely on changing a phase of a fluid. You literally have to change a vapor to a liquid, or a liquid to a vapor. These phase transformations are the absolute heavy lifters in modern power and refrigeration cycles.
Section 2. Film versus Dropwise condensation.
Let's think about a vertical flat plate exposed to condensable vapor. We basically get a tale of two very different condensation personalities here. First up, we've got film condensation. This is where the liquid completely wets the surface, creating this smooth, continuous film that acts as a really stubborn thermal resistance barrier. On the flip side, we have dropwise condensation. In this case, the liquid doesn't wet the surface at all. Instead, it forms these random, independent droplets, which leaves massive portions of the plate completely exposed directly to the vapor. The visual proof of this is absolutely striking. Just look at the left side. Steam is forming this continuous, blanket-like film right over clean copper. But over on the right, we're seeing distinct droplets forming on a gold-plated copper surface. Because that gold layer physically stops the liquid from fully wetting the surface, those droplets are able to form, merge together, and just run right off. Here's the kicker, and why engineers care so much about this. Dropwise condensation is highly preferred because it can actually achieve heat transfer rates up to 10 times higher than film condensation. 10 times! It's a complete game changer because you bypass that stubborn thermal film barrier. The catch, though, it's extremely difficult to maintain out in the real world because most surfaces, well, they eventually just become completely wetted over time.
Section 3. Math of the condensation film.
Because film condensation is the stubborn reality in most industrial systems, we have to know how to predict its behavior. And this brilliantly illustrates the physics first proposed by Nusselt. As that condensation film moves down the plate, its thickness, which is that little delta symbol there, starts to grow. Nusselt realized that the downward weight of this fluid element is perfectly balanced by two opposing upward forces, viscous shear and the buoyancy of the displaced vapor.
Now, I could definitely throw some massive integral equations your way, but let's skip the headache. This table cleanly isolates the exact variables engineers actually care about. By combining things like fluid viscosity, the density difference between the liquid and the vapor, and thermal conductivity, we can calculate a dimensionless group called the condensation number, and that little number lets us reliably predict heat transfer whether the film flow is smooth and laminar or heavily turbulent.
Section 4. The 6 regimes of boiling.
All right, shifting gears from a cooling vapor to a liquid violently heated above its saturation temperature. And this isn't just a simple single-stage event. This curve maps out a shocking escalation of thermal chaos. Plotting heat flux against temperature excess, notice how we start way over on the left with gentle free convection. Then it rises into nucleate boiling, hits this extremely dangerous peak, plummets down into a highly unstable transition region before finally leveling out into stable film boiling, where thermal radiation actually comes into play.
To anchor that graph in physical reality, check out this submerged heated copper rod. It literally visualizes the curve we just looked at. Because it's heated aggressively from the right side, you see quiet convection on the cooler left end, building into intense nucleate bubbles right in the middle, and ending in violent film boiling on the far right. It's the whole spectrum at once.
Looking closer at methanol boiling on a horizontal copper tube, we can actually watch these exact regimes progress. Over on the left, we've got the vigorous, healthy bubbles of nucleate boiling, doing what it should. In the middle, things get messy. The bubbles start dangerously coalescing in transition boiling. And then on the right, a complete, suffocating vapor film has enveloped the tube entirely.
When that vapor film completely coats your heating surface, you get what we're looking at here. Highly active, turbulent film boiling. The heat now has to conduct through this vapor film before it can even touch the liquid.
That massive thermal resistance makes the equipment's temperature absolutely skyrocket. This is a huge hurdle for heat transfer systems because the surface temperatures needed to maintain this can easily exceed the melting point of the metal itself, which leads to catastrophic equipment burnout. To mathematically tame all this intense chaos, specifically aiming for that preferred nucleate boiling phase, engineers rely on the famous Rosenau equation. They carefully plug in precise variables like liquid viscosity, temperature excess, and surface tension to prove that even in the middle of thermal chaos, everything still obeys these strict laws of physics.
Section 5. The drama of bubble growth.
Let's zoom way in, past the macro equations, down to the intense microscopic drama of a single bubble. Because this tiny thing is the engine making all these high heat transfer rates possible. A microscopic bubble is essentially a delicate battlefield. The outward pressure force from the internal vapor is constantly fighting against two things: the inward pressure of the surrounding liquid and the literal surface tension wrapping around the interface. If these aren't perfectly balanced, the bubble just explodes or collapses.
So what's the secret to a bubble actually surviving? It relies on a metastable thermodynamic state. This state explains the exact why of the drama. For a bubble to grow and eventually escape, the surrounding liquid has to be superheated, meaning the liquid is literally hotter than the vapor inside the bubble. No way, right? But this forces heat to conduct inward, allowing evaporation to take place right at the interface. Without this superheated liquid, the bubble would just hopelessly collapse right back onto the surface.
So I leave you with this final thought. The next time you're standing in your kitchen waiting for a simple pot of water to boil on the stove, take a really close look at those bubbles forming at the bottom. Think about the epic battle of surface tension, the metastable thermodynamic states, and the massive mathematical forces operating right in front of your eyes. It really makes you wonder, what else in your everyday world is hiding incredible thermodynamics right in plain sight? Thanks for joining me on this explainer, and keep questioning the physics of your world.